Yeah.
Welcome everyone. I'm very happy to introduce Ayse Nur today. So she's a junior researcher at INRIA Center of Bordeaux, and she is mostly working on mixed integer optimization problems and optimization under uncertainty with special focus on robust and stochastic optimization. So she has several papers on two-stage robust optimization, and I'm very happy to have her here today to talk about her new work.
Yes. Well, thank you, Yanis, for the introduction, and thank you to you and Reza for the organization of these webinars and for the invitation. Um, so I wanted to talk about today uh, some recent work that we have done with Michael Poss, who is also a researcher from CNRS. And this is on uncertainty reduction in static robust optimization. I'm assuming that most of the people here will be familiar with what static robust optimization is, but maybe uncertainty reduction is a new keyword for you. So I'll start by describing what this exactly means. This actually is a kind of decision-dependent uncertainty paradigm. So to talk about this, I'm going to start with talking about the classic robust optimization paradigm that I describe like this. So this is an optimization problem over a linearly constrained set in which some of the data is affinely dependent on these primitive uncertainties psi, which live in this polyhedral uncertainty sets. So this is quite classical, and we all know and love this kind of problems because they can be reformulated as deterministic problems that are polynomial in the size of the input. So this is quite a common optimization under uncertainty paradigm. But this kind of paradigm, it cannot model any sort of interactions between the decision maker and the uncertain parameter. And one of the ways that the decision maker could potentially interact with the uncertainty is through what's called the decision-dependent uncertainty set. So in this modified problem, we introduced the decision variables X, and then these decision variables entered the description of the uncertainty set. And here you have a specific structure where this dependence is only through the right-hand side. It's through this affine function. It's through a matrix delta. So the decisions X will change the right-hand side of the uncertainty set's constraints. So there are several reasons why it would be interesting to study such problems. The first of which being that in certain applications, there is actually some effects of the decisions on the realization of uncertainty. So the uncertainty is kind of endogenous. So we can, for instance, think about network design. In network design, once you construct the network, the users will probably change their behaviors depending on the structure of the network. So the design of the network will have an impact on the future demand of the network. So this might be taken into account through this kind of interaction with the uncertainty set. So here you see that the matrix delta is, either positive or negative. So it can have a positive or negative impact on the uncertainty. So we can also imagine that the decision maker has some proactive actions that he can take that would reduce the uncertainty, right? So it's not only increasing the uncertainty, it can also be decreasing the uncertainty. This kind of a model, it can also appear as a modeling tool in certain contexts, and I will talk a little bit about this when I talk about the literature. And this specific decision-dependent structure, a robust optimization problem with this structure, it was shown to be MP Hard and Noadani and Sharma. All right, so here we will be interested in a more specific decision-dependent structure. And so we call this uncertainty reduction. So basically here, the idea is variables that will interact with the uncertainty sets, they will only touch the right-hand side of some upper bound constraints. Okay, so here V and W are non-negative parameters and Xi are non-negative uncertain parameters. So when X is equal to 0, these parameters will go up to V plus W, and then when it's equal to 1, they can only go up to V. Of course, all of these are element-wise upper bounds that are applied on the vector Xi. And the motivation behind such a model being that you can take some proactive actions such as repairing machines or doing some investments on tools that would make more precise measurements in order to reduce the extent of uncertainty. And here, for the following, we will assume that uncertainty reduction is all or nothing in the sense that these X variables, they will be assumed to be binary. Okay, and we can remark that if the value of this parameter Vi is equal to 0, then when Xi is equal to 1, the corresponding uncertain parameter will completely reduce to 0, so its effect will be eliminated completely from the problem. Okay. So then we will consider in the following robust optimization problems under this uncertainty reduction paradigm, and I'm going to write these problems under this form. And here you can realize that I only considered objective function uncertainty. So this is a min-max problem where we consider an affine function of the uncertain parameter in the objective function. And this is the only uncertainty that I'm going to consider in my problem. But this is, of course, without loss of generality. It's only to facilitate the exposition of our results. Okay, so I'm going to first talk about a small example just to make sure that we all understand the problem and then to motivate also the study of such problems. So we'll look at the shortest path problem on this graph defined here. So this graph, the data that you see on the arcs, they are subject to a 50% deviation through these parameters Xi that's defined here. And the parameters Xi live in this decision-dependent uncertainty set. So we hear that the sum of Xi should be less than or equal to 1. And then their upper bounds are equal to 1 when there is no uncertainty reduction. And depending on the uncertainty reduction, it can go down to 0, 2. Okay, and the set X, which controls the uncertainty reduction, will constrain it to choose at most one arc, okay, to protect. And obviously the set Y will contain the flow constraints. So now if we look on this problem to the nominal optimal solution, meaning that the optimal solution not taking any uncertainty into account, it would be the path SCCT, which has nominal cost 95, and its worst case cost will be 127, with the cost of this arc will going up by 50%. Now, if we look at the robust solution, meaning that we don't take into account any kind of uncertainty reduction and only the classical robust optimization paradigm where all of the upper bounds are equal to 1, then we will choose the path SEFGHT. And the nominal cost of this path is 97.4, and its worst case cost is 110 something. So this is quite classical, right? In robust optimization, you lose some in the nominal cost, but you gain in the worst case cost. So you degrade a little bit the quality of the nominal solution, but the worst case solution, worst case objective value is improved. Now, if we consider the uncertainty reduction paradigm, we see that the optimal solution is taking the path SECT, and I'm protecting the arc CT because it has the higher cost and therefore the higher deviation. So when we protect this arc, its deviation will be reduced from 1 to 0, 2. So it will only deviate by 0, 2. And then the remaining budget of 0.8 here, it will go on to ArcEC. So the nominal cost of this solution is 95.3, whereas the worst case value is 18.1. And you see that there's something quite interesting here in the sense that with respect to the robust solution, the uncertainty reduction solution, it has both better nominal value and also better worst case value. This happened because obviously we considered that we could reduce the uncertainty, and so the worst case value is sort of impaired while the adversary is sort of impaired, and that allowed us to choose a lower cost nominal solution. But of course, here we didn't take into account the potential cost of using this variable. So the uncertainty reduction doesn't have any cost. If it had some cost, this value could potentially go higher. But this is still quite an interesting example showing that there is value in considering such interactions with the uncertainty set. And of course, being able to solve such problems, it would also help you determine the value that you would put in any sort of proactive actions that you could do to control uncertainty. Okay. So next, I wanted to talk a little bit about what's happening in the literature with respect to robust optimization problems with decision-dependent uncertainty sets. So there aren't a lot of work, but there are a few papers that talk about such models, and I categorize them as general models and the kind of papers where decision-dependent uncertainty sets show up as modeling tools. So here we have a paper by Noadani and Sharma, quite recent, that introduced this uncertainty reduction paradigm and worked on mixed integer programming models for this problem. And then recently, Zhang and Wang introduced adjustable robust optimization problems with decision-dependent uncertainty set, and they proposed solution algorithms for those problems. So this is based on the generalization of the famous constraint on column generation approach. And then you have some papers where decision-dependent uncertainty sets are used to specific ends. For instance, Spacey et al., they will use this to model a certain software partitioning application. Michael also has some work where the budgets of the budgeted uncertainty sets, this famous gamma parameter, it's adapted to the cardinality of the solution. And then you have, in the context of k-adaptability problems, the work by Ana Susanto and co-authors, where they use these kind of decision-dependent uncertainty sets to model the feasibility of the k-adaptable solutions. And we also know that recently the relationships between robust optimization and bilinear optimization, it was the subject of some work. So we know that there are close connections between decision-dependent uncertainty sets and robust optimization and bi-level programming, as well as generalized semi-infinite programming. But despite all of this existing work, there is obviously a lot of open questions that we don't know answers to. So here we wanted to study some of those questions. So one of the first things that we wanted to look at was what was happening to robust combinatorial optimization problems under the uncertainty reduction paradigm. So what I'm calling robust combinatorial optimization is a special case of the general problem where you have the set Y, which is a combinatorial set, so the variables are binary. And then the structure of the dependence of these cost coefficients on Xi is restricted in the sense that you can only have a diagonal matrix F here entering the objective function. And actually, when you do this, you will have one Xi parameter interacting with one Y variable, okay? And here we will also assume at first that the uncertainty set has only one constraint, a complicating constraint in this form, and then obviously the upper bound constraints. Okay, excuse me. So on these problems, the first thing that we were able to show is that they are actually NP hard. And this is the case even when the underlying combinatorial problem over Y is polynomially solvable. And this might be kind of surprising because if we think about robust combinatorial optimization without decision dependence, meaning that if we fix the vector X, then the remaining problem is known to be polynomially solvable whenever the underlying combinatorial optimization problem is polynomially solvable. And this is this famous result by Bertimes and Sim, where they're doing this consecutive solution of combinatorial problems in order to obtain the solution of the robust combinatorial optimization problem. So this is kind of a negative result. But we were able to identify a special case in which we can, again, obtain a result that is similar to this classical result by Bertimes and Sim. Sorry. So we'll consider the case where the set constraining the uncertainty reduction variables is unconstrained. And in this case, we will be able to develop an algorithmic approach that relies on repeated solution of combinatorial problems of this form, each time with a different cost vector. And as a result of this algorithmic approach, we will be able to show that if the combinatorial problem can be solved in polynomial time for any given cost vector, then the robust combinatorial optimization problem under the uncertainty reduction paradigm is also polynomially solvable. And so formally, we'll write the result like this. And in the result, you will see that we talk about n+1 deterministic problems. So this number is the dimension of the combinatorial set. So we will need to at most solve as many deterministic combinatorial problems, meaning that if the combinatorial problem is polynomially solvable, then our algorithm as well will be polynomially solvable. Okay, so how does this work? So for the proof, I'm going to assume that the parameter V is equal to 0 and the matrix F is identity. So I'm going to come back to this kind of problem where V has disappeared from the right-hand side here and F has disappeared from the objective function. Okay. So, and in the following, in order to get rid of some of the notation, I'm going to assume that X and Y are combinatorial sets, and I'm not going to write this notation here. Okay, so the first thing that I'm going to do on this problem is to write the linear programming dual in order to obtain this model with the dual variables theta and pi. The objective function expressed in terms of these variables, and then of course the constraints that are coming from the constraints of the uncertainty sets. Okay, so if we study this kind of constraint and this variable pi j, we'll realize that if x, y, and theta are given, since the cost coefficients of these pi variables are non-negative, these variables will tend to their lower bounds. They will want to be as small as possible. So since each of these variables is lower bounded by yj minus aj theta, either this value is non-negative and so it's lower bounds by j, right? Or this value is negative and so pi j is lower bounded by 0. So as a result, we obtain that in any optimal solution, the value of this variable pi j will be equal to the maximum between 0 and this expression here. Okay, so we can plug that in. Now we have the problem over 3 variables. We got rid of pi j's. But the thing is, this max function, it's a nonlinear function of the decision variables y, and that we don't like as much. So we'll try to get this y out of this maximum function. And the classical trick for that is to use the fact that y variables are binary. So we actually have that if this variable is equal to 1, then the expression is equal to the maximum between 1 minus aj theta and 0. And if this variable is equal to 0, then the expression is exactly equal to the maximum between 0 and minus aj theta. And so this can be linearly expressed in variables y using the variable y and its complement. So you see here that if yj is 1, then this term will survive and we'll get rid of this term. And if yj is equal to 0, then this term will survive and we'll get rid of this term. And so I will exactly have the results that I had here. And so I'm going to go ahead and plug this into my objective function. And now I have an expression that is linear in y. So I need to, but my theta is still in the maximum function, right? But what we realize is that if x and y are fixed, then the remaining expression here in theta, it's actually a positive combination of piecewise linear convex functions, because each of these max functions, they are piecewise linear convex functions, and then the cost coefficients here, wj, 1 minus xj, and yj, are all non-negative, okay? And so as a positive coefficient combination of piecewise linear convex functions, this whole function over theta is itself indeed piecewise linear and convex. So visually, I actually looked at an example here where I put in 4 piecewise linear functions with some coefficient 1.5 and plotted the function over some range of theta. And here you see that the function itself is piecewise linear and convex. And we also realize that the slope of this function will only change at the breakpoints of the individual functions that it's making up this combination. So if we then look at the individual piecewise linear functions themselves, their breakpoints, so for the 1 minus aj theta, it will be 1 over aj whenever aj is strictly positive. And obviously, when aj is strictly negative, this is all non-negative, meaning that there will be no breakpoint. And for the other guys, the only breakpoint is actually 0. So because otherwise, this function is affine, right? So that means that the only values that we need to consider for this theta variable are either 1 over aj's or 0. So we can actually go ahead and plug that in. And in the worst case, we realize that all of the aj's will be strictly positive, meaning that we will need to evaluate all of the 1 over aj's. So we will have n values here and 1 value here. So n plus 1 in the worst case solution of these problems. So each time fixing, obviously, the value of theta. So what are these problems? These are actually deterministic problems, right, over x and y. But we have bilinear terms. Yeah, so it's here. Because of the multiplication between x's and y's here. So this indeed is not a big problem, because since these are binaries, you can always use McCormick linearization to come back to a mixed integer linear programming problem. But the thing is, we won't be able to use any kind of solution algorithms that we have for the ground combinatorial problem that is written over y. So that's sort of not nice, and we don't know what the complexity of this combined problem over x and y is. So the question we asked ourselves was, are there any cases where we can get rid of this bilinearity so we can get back to a combinatorial problem over Y? And it turns out that if the set X is not constrained, then we can actually calculate the optimal solutions over X in a closed form so that we come back to a combinatorial problem over Y. Okay, so in order to do that, I'm going to go from this problem to the same problem just written in a slightly modified way, where I tried to put all of the terms that involved Y variables in front, and then all of the terms that involve X variables or the bilinear terms after. And so once I do that, I realize that I can actually solve this problem like a two-stage problem, in which the first stage variables would be Y, and then the second stage variables would be X, and the second stage variables, they will be decided after the Y values are fixed, okay? So if I do that, so let's assume that I fix one of the Y variables, then my problem over X here, it will look something like this. So you see here that it's each time cost coefficients that is completely determined by the theta and Y variables that are fixed, plus some of the data that multiplies the variable xj. So we see that if this set is constrained, then clearly this problem is another combinatorial optimization problem, so we cannot hope to obtain its optimal solution in closed form. But if we assume that the set is unconstrained, then what happens is that the minimum over these variables, so minimum of the sum, can be also written as the sum of the minimums over the individual variables, because there is no constraint that is connecting different X variables, so we can optimize over them individually. So in that case, it actually suffices to concentrate on one of these problems each time over a decision variable that is binary, okay? So that one should be easy. So if you look at this problem now, we easily see that if this coefficient here is strictly negative, then the optimal solution will be equal to 1. And if the coefficient is non-negative, then the optimal solution will be equal to 0, okay? So that's exactly what I'm going to write. So that will, of course, also depend on what the values of Y variables are. So if the Y variables is equal to 0, then I'm going to obtain that, okay, this term will survive and this term will survive. So I'm going to obtain that the optimal value is equal to this guy, which this guy being the minimum between 0 and the expression that is inside the brackets. Okay, and when the Y variables is equal to 1, then this term is going to survive and this term is going to survive. So I'm going to obtain the optimal value as the minimum between 0 and the expression within the brackets. And once again, similar to what we have done before, this can also be written linearly in Y. And so we write it in this way, and you'll see that when Y is equal to 0, then this term will survive as here. And when Y is equal to 1, then this term will survive as in here, okay? And so now we are able to state the final result. Putting all of this together, we will be able to solve the problem when the set X is not constrained as the solution of n+1 problems that present in this form, each time fixing the value of theta to one of these values here. And you see that the cost coefficients here, they are completely determined by data. Okay, and this problem is indeed in the same form as the combinatorial problem. meaning that obviously if the combinatorial problem is easy to solve for any cost coefficient, then we have n+1 solutions of this combinatorial problem. So we'll have a combinatorial algorithm. Okay, so just to remind what was done, in order to do the proof, I assumed that V was equal to 0 and F was the identity matrix, but the result actually holds for any value of non-negative V and any diagonal matrix F. The polynomial complexity result holds in that case. And the algorithmic approach itself, it can be extended to the case where there are multiple constraints, complicating constraints in the uncertainty set, as well as multiple constraints in the problem that are affected by uncertainty. But of course, in those cases, the different values of theta that you need to consider, you need to cross them across constraints of the uncertainty set or across constraints of the problem. So you have this combinatorial thing that comes into play. And in those cases, the complexity of the problem, the number of deterministic problems that you will need to solve, it will actually increase exponentially in those numbers. So either the number of constraints in the uncertainty set or the number of constraints that are touched by uncertainty in your problem. Okay, but this is anyways a nice result in the sense that we were able to show that there was a polynomial time approach or an algorithmic approach in certain cases, and especially when the problem is combinatorial and there are a couple of assumptions that are satisfied. But obviously not all of the problems that we want to look at will satisfy these assumptions. And in those cases, it might also be interesting to consider mixed integer programming reformulations. And so that's what I want to talk about in the second part of the talk. So I'm going to come back to this more general problem where we don't have the assumption that Y is binary anymore. And I'm not restricting the matrix F to be diagonal. And I'm not restricting the set X to be non-constrained, okay? So if you look at this problem, it's kind of easy to see that you can do the classical reformulation tricks once again. So if X and Y are fixed from outside, then this problem over here is a linear programming problem. So you can use linear programming duality. And what you will recover is multiplications between these terms involving X and the dual variables pi. And so you will have a bilinear programming formulation. And then you can, of course, think about linearizing these terms, which will require, since X are binary, it will require you to calculate some bounds on pi variables. And so that can be inconvenient because it might be difficult to calculate these dual bounds. And so one of the ideas that was proposed in the literature was to transfer the decision dependence of the uncertainty set from the right-hand side to the objective function so that the X variables would not be multiplied by dual variables. Okay, so in order to execute that idea, we will write an uncertainty set that is slightly modified with respect to the original uncertainty set. So here in this uncertainty set that I'm going to denote by psi bar, I am going to split the original uncertain parameters into two, psi1 and psi2. So the constraints, sort of the budget constraints that will apply to the sum. And then variables psi1 will be bounded by V, and variables psi2 will be bounded by W multiplied by 1 minus X. Okay, and the first kind of observation we can have is that the worst case value over the original uncertainty set is equal to the worst case value over this split uncertainty set. Because any realization that's here, we can represent it here through sum of psi1 and psi2, independent of the value of x and y. Okay. But what's nice about this representation is that in this representation, whenever x is equal to 1, the uncertain parameter psi that corresponds to it will be equal to 0. And that will help us write some reformulations. So the first reformulation that will use this kind of logic, it was first introduced by Noedani and Sharma, and we generalized it a little bit. It says that the worst case value of the original adversarial problem is equal to the worst case value of this modified problem. And in this modified problem, you have two things. The first thing is that the uncertainty set, it's the split uncertainty set with the value of x fixed to 0. So if we come back here, we see that when x is fixed to 0, this set is completely independent of the decisions. And so psi1 and psi2 will be free to take any values that they like up to their upper bounds, of course. And the second modification that is done is that variables psi2 are multiplied by this negative coefficient that depends on x. So in order to understand the equivalence between the two things, first consider that x is equal to 0. Okay, so this is the case where there's kind of no reduction of uncertainty. And in that case, we actually have established that this problem was equivalent to this problem. So that's one. And the second thing is when x is equal to 1. So this is, of course, component-wise. And in that case, you are actually multiplying this variable psi2 by some quite negative value. So this matrix pi bar here, it should be thought of as a big M coefficient that would discourage the use of variables psi2 whenever x is equal to 1. And it turns out that if you choose these big M coefficients as the maximum value of the dual variables in the dual formulation, then you have a valid big M. So whenever x is equal to 1, you can show that psi variables are equal to 0. But once again, so here, the nice thing is we were able to pass the decision dependence from the right-hand side to the objective function. So we won't have these bilinear terms anymore. But we will need to calculate these upper bounds from the dual side. So that might not be quite practical. And it turns out that if we have some non-negativity assumption on the constraint matrix defining the uncertainty set, then these coefficients can indeed be replaced by some bounds that are obtained from the primal side. So this is obtained as the maximum value of this affine function of y that is maximized over y. So if this value is non-negative, then you take this value. Otherwise, you just take 0. So the implication of this result is that, for instance, in the special case that f is equal to identity and y is a combinatorial set, then we have that this big M coefficient matrix pi is equal to the identity. So you recover terms in y minus x, something like that. Okay, so this is the first approach. And the second approach that we proposed was once again stated under the assumption that the constraint, the coefficient matrix of the constraints of the uncertainty set is non-negative. And in that case, we have once again the equivalence between the worst case value of the adversarial problem and the worst case value of this problem, where once again, we're fixing the split uncertainty set with x is equal to 0. So the split uncertainty set psi1 and psi2 are bounded simply by v and w. But here we are adding in the objective function the multiplication between 1 minus x and psi2. Okay. So to see the equivalence once again between these two formulations, when x is equal to 1, we hope to have xi2 is equal to 0, and when x is equal to 0, we hope to have equivalence, right? So when x is equal to 0, the equivalence was established before, and when x is equal to 1, what we would like is to say that xi2 that corresponds to it is equal to 0. And that's where we will need this assumption that the matrix A is non-negative. Because otherwise, if A is not non-negative, it might be that even if the cost coefficient of this variable xi is equal to 0, the xi2 variable might want to be positive in order to increase the xi1 values, okay? But when the coefficient matrix A is non-negative, this doesn't happen, so we can establish the equivalence between these two formulations. So once again, when we have this, what's the advantage? The advantage is that x is transferred from the right-hand side to the objective function. So when we dualize, we won't recover multiplications between dual variables and x variables. But in this version, we will actually recover multiplications between x variables and y variables. But once again, we will be able to linearize this using the McCormick linearization. And the bounds that we need to calculate will purely depend on the y variables from the primal side and not the f times y that we need to calculate. So it could be more practical to calculate these ones. We were also able to show that this reformulation approach, it can have a arbitrarily better linear relaxation compared to the big M approach that we presented previously in certain cases. But of course, the choice between these two formulations, it's kind of complicated in the sense that in the second formulation, you will introduce some additional variables because of the bilinearity and because of the linearization of this bilinearity. So the improved linear relaxation, it comes at the expense of increased number of variables. So the solution time, it will depend on a certain number of factors like the quality of the relaxation, the quality of branching, the number of variables, the effectiveness of heuristics, so on and so forth. So the choice between the two is not essentially very clear just by looking at the formulations like this, and one would need to test in order to have a better understanding. Okay, so I'm now going to present some numerical results and I will be able to conclude. So the results I'm going to present are on the shortest path problem. So the set y represents the shortest path, and the set x, the uncertainty reduction variables, are unconstrained. And the uncertainty set here is the classical budgeted uncertainty set that we modified through uncertainty reduction. Here you see that the cost of each arc, it can deviate up to 50% once again. And when there is uncertainty reduction, the upper bound of each of the psi variables, it will go from 1 to 1 minus gamma ij. So on this problem, we compared our algorithmic approach to the mixed integer programming approach based on the big M reformulation, because we realized that on this problem, the big M reformulation and the reformulation that we proposed had the same linear relaxation value, and the big M formulation had less variables, so we didn't actually test the second formulation. And then we did the tests both with a commercial solver and the open source solver. So the commercial solver was chosen as Gurobi and the open source solver was Heise. And to implement our algorithmic approach, in order to solve the shortest path problems, we use the light graphs package of Julia. So everything was coded in Julia.
Ayse, one small question. In your setup, the y's are the shortest path.
Yeah.
And they are not influenced by the x?
No, so what's influenced by the x is the uncertain parameters that touch the cost of the y's.
Okay. Thank you.
Sure. So the first kind of numerical results that you're seeing here is the ratio between the solution time of the MIP approach using Gurobi divided by the solution time of the algorithmic approach. And each of the data points that you see here, it was obtained as the geometric average of 10 randomly generated instances. So we use the same generation approach as was in Nodanian Sharma. And we presented these data points as a function of increasing instance size. So you're seeing here the number of nodes in the network. And the specific data is presented here. So the cost coefficients are based on Euclidean distances. And then the cost of uncertainty reduction is 1 throughout. The budget is fixed to 2, and the reduction parameter is fixed to 0.2 for everyone. And the time limit is 2 hours. So in this set, all of the instances were solved to optimality by both approaches. But you see that the algorithmic approach was between 3 to 5 times, I think, faster than the MIP approach in this case, using the commercial solver Gurobi. And then we have the same experiment with highs. And here you see that we were able to look at some smaller instances compared to the first experiment, because for larger instances, highs was not able to solve all of the instances to optimality, so we had to cut them off at some point. And here, once again, you're seeing the geometric average of ratios. So the speed up factor here is actually 2 orders of magnitude. So the algorithmic approach is 2 orders of magnitude faster than the mixed integer programming approach using the high solver. So the conclusion being that, of course, the comparison between such approaches is highly dependent on the quality of the solver, the quality of the mixed integer programming formulation that you have, and it can be problem specific, but we see that at least on these problems that we consider, for which the solvers need to be able to have quite good algorithms, the algorithmic approach was actually paying off quite nicely. Okay, so I'm going to be able to conclude with some remarks. So I hope to have convinced you that these problems, so the robust optimization problems with decision-dependent uncertainty sets, and in particular the uncertainty reduction paradigm, are interesting problems to study, so we should explore them more. But one of the things that we understood quite quickly is that they lead to difficult problems. And in the case of robust combinatorial optimization problems, they're often more difficult than the static robust optimization problems without considering decision dependence. But we were able to find some special cases in which the problem can still be solved in polynomial time through an algorithmic approach. So I think what we have done here is only scratching the surface. So there are many things that you can do on these problems, including exploring further algorithmic approaches based on bi-level programming, based on cutting planes, based on what have you. We can also consider some more general uncertainty dependent structures. For instance, the affine decision dependent structure. And obviously the integration of decision dependent uncertainty sets within adjustable robust optimization remains also as a big open question. And so with that, I think I want to thank you for your attention. And then if you have any questions, please do not hesitate. Thank you.